talking about the lesion-symptom mapping using machine learning. He's talking, sorry.
Hello. Thank you very much for giving me the opportunity to be at this great symposium. This is a work that I've been doing as a neurosurgeon, and I am collaborating with Bertrand Thirion, who is a data scientist in RIA. So the problem that we face as a neurosurgeon is, can we predict the cognitive outcome of an intended resection? So let's say we have this patient with this tumor, and we test a cognitive function with test A, and the score is X. And what we would like to know is, if I resect this, or this, how will evolve the score of the test A? And of course, to address this question, we need to extract all information from past cases. So we have to rely on a series of N patients for which we have all the MRIs and all the scores of the test. And then after the surgery, we have the post-operative MRIs and the new scores of the test that we want to study. And in 20 years ago, there has been a new way to approach this kind of problem of lesion symptom mapping. And it was based first on the segmentation of the surgical cavity and registration in a standard template, the MNI template. For example, Hans algorithm is a good algorithm to do that. So you end up with all your patients, all the surgical cavities are registered in the same anatomical space, and you know if the patient has a deficit or not. And then you can review all the voxels one by one, and for each voxel, you do a small contingency table, and with a kind of Fisher exact test, of course, because there are a lot of voxels, you have to correct this, but the principle is here. You decide if this voxel correlates with the presence of the deficit or not when the voxel is damaged. But of course, there is two drawbacks of this mass univariate voxel-based lesion symptom mapping. First, lesionally, voxels are not independent. A lesion is a biological process, so that when one voxel is damaged, there is a high chance that surrounding voxels will be damaged as well. So you cannot treat voxel independently from each other regarding the nature of the lesion. The second problem is that functionally, voxels in the brain are not independent. Two voxels in the brain are not working independently. If one voxel is damaged, it's not the same if another one in some other part of the brain is also damaged or not. And I think that everyone was aware of these limitations, but not completely aware how much this could lead to mislead us to wrong conclusions. And there has been this important paper published in Brain in 2014, showing that if you assume that a function is supported by two spatially distant areas, and you apply this mass univariate voxel-based lesion symptom mapping, you can wrongly conclude that the real important area is in between the two areas. So you completely miss the location of the important areas that you want to identify. So these authors said that if you want to solve this, you have to use multivariate approaches. But multivariate approaches, what is multivariate approaches? Here you put all the patients in columns, all the voxels in lines, 0 if not damaged, 1 if it is damaged. And by machine learning, you want the machine to learn how to predict the first line based on all other lines. So that when you give to the machine a new column, it will be able to predict if there is a deficit or not. But there is an important drawback of multivariate approaches, of all multivariate approaches, and it is called the curse of dimensionality. In fact, to solve the problem, the machine needs a huge number of examples, and this number increases non-linearly with the number of dimensions. And here the number of dimensions is the number of voxels, which is between 100,000 and 1 million. So there are two solutions to solve this issue of the curse of dimensionality. The first is to increase the number of cases. That's the reasons of big data. And the other one is to try to reduce the dimensionality of the problem by using our knowledge about the brain functions. And that's what I will try to show you as an example. So I operated this case, a lady of 40 years old, and I checked several functions during the surgery, an awake surgery. And 4 months after the surgery, the resection was complete, but the patient was unable to perform the trail making test part B, which consists to join in ascending orders numbers and letters 1, A, 2, B, and so on. So she was able to do that before the surgery, and now she's completely unable to do it. So we tried to understand what happened. So we had the resting state MRI of these patients before the surgery. So we identified a network, a right fronto-parieto-temporal network. And this network completely disappeared after the surgery, despite the fact that the tumor and the resection cavity spared the cortical areas of this network. And when you look at the tractography, the structural connectivity, what happened is that during the surgery, I cut all the connections between 2 pairs of these 3 frontal, parietal, temporal areas. So we disconnected a network of 3 areas. So this gives me the idea to generalize a network lesion, a network level lesion symptom mapping. Assume that you know that a function is supported by the green network. And you know the streamlines, the structural connectivity supporting this network. Now, among the blue streamlines, you can select all the magenta streamlines which are going through the lesion in orange. Okay, so the lesion will destroy a certain number of streamlines supporting the structural connectivity of the green network. And then you can compute an index of network disconnection. The simplest way to do it, but there are several others, is to compute the ratio of the number of pink streamlines divided by the number of blue streamlines. And by doing so, if you do it on a number of network of interest, you drastically reduce the dimensionality because the dimensionality becomes the number of network of interest. So for example, in the case that I show you, we can use the parcellation of the brain. If you have no a priori of the network, if you don't know which set of areas you have to select, you can parcellate the brain in network based on resting state connectivity. And you can compute for each of the 17th network, which one are especially disconnected. So these come up with the network 6, 7, 12, 13, and 16. They have been disconnected by the surgery more than other networks. And what is interesting is that in a second case, with exactly the same location, the same tumor location, this time we tested the trail making test part B intraoperatively. So the patient was tested in awake surgery on this test. And in fact, we found that when we stimulated in the depth of the resection with electrical stimulation, he was unable to shift from numbers to letters. So there was a functional site in the white matter of the resection. And of course, the patient had no postoperative deficit because we stopped the resection when the electrical stimulation generated this impossibility to do the shifting. And when you look at the disconnection for the surgical cavity, there was barely no disconnection. But what is interesting is that if you add to the surgical cavity the small volume corresponding to the virtual cavity induced by the electrical stimulation, then you find again that network 12, 13, and 16 are especially disconnected by this additional small sphere corresponding to the stimulation. And these three networks fit well with the fronto-parieto-temporal network that has been highly disconnected in the previous case for whom the patient did not recover. So this is now our roadmap of the disconnect projects. We are working on a series of 120 patient cases. We have computed for each cases 51 indices of network disconnection because we have cortico-cortical connections, striatocortical and thalamocortical. So we have 17 networks for each of these kind of connections. We have the postoperative change in the trail-making test part B. We have created a synthetic ground truss. That is, we have artificially decided that there would be a deficit if the disconnection of network 12 is higher than 5% and the disconnection of network 13 is higher than 5%, so that we have a ground truss on which we are currently testing several algorithms, hierarchical decision trees, random forest. That's where Bertrand Thérion is absolutely fantastic because he will help us to find the optimal algorithm. And once we have done this, we will apply the best algorithm to the real data and try to see if we can indeed predict the change in the trail-making test part B, depending on the surgical cavity. So in summary, the clinician has an important role to play because from single case analysis, is able to infer a pathophysiological hypothesis. And this pathophysiological hypothesis will help to reduce the dimensionality of the problem by including our knowledge of connectivity data of how the brain is functioning, and by including the information from patient images, because of course, the method can work if we are using the resting states and the tractography of the patient himself. So thanks to this pathophysiological hypothesis, we can reduce the huge dimensionality of the images to a relevant set of predictors, which is about 100 predictors, let's say. And something that I did not discuss, but the functional scores, of course, I illustrated just with one score, one cognitive score, but in fact, patients have about 100 scores on each cognitive evaluation. So we can also use a representation of reduced dimensionality. This reduced dimensionality might correspond, for example, to broadly working memory, inhibition, set shifting, and so on. So different broad categories of cognitive functions. And then we have to find the best machine learning algorithm so that with this relevant set of predictors, we can predict how will evolve the functional scores. And if the prediction is high, this in turn will validate our initial pathophysiological hypothesis. So thank you very much, and I am happy to answer any question.
Thank you very much, Emmanuel. Brilliant. I think that someone rose the hand. Any questions from the audience?
So maybe I just have one small question to Professor Mandonnet. I'm curious to know how in your probabilistic atlas, when you reduce, so when you collect all the data of several brains to a common space, how do you account for gyral anatomy? So how can you be sure that that very voxel corresponds to the post-central gyrus in every patient and not to the supramarginal, for example?
So we are using when we put everyone in the same anatomy. So we are using Hans algorithm, and of course we can check manually that the registration process went correctly. So manually we can check that indeed the main landmarks are correctly aligned. And I must say that because it's a long time ago, I've been working with registration algorithm in the context of brain lesions and brain tumors. And previously, the algorithms were not so good because of the deformation of the surgical cavity. But now with Hans algorithm, I must say that the results are pretty amazing. And I think it's not perfect, of course, but it's probably sufficient for what we want to do.
So you have still to manually visualize each of them to be sure.
Yeah, it's better to make sure that everything went well during the registration process.
Okay, thanks a lot for your work. Very excellent work. Thanks again for coming.
Thank you.
So I don't see any questions in the chat. Or maybe yes.
Let's move on to the next speaker, maybe.
Oh, there is just a last question I see. Was there any prognostic trade-off for lower resection in your subjects? Do you think that we can use prognostic factors for better learning algorithms?
For the first question, we would like to know indeed if we can, with this method, modulate what we would like to resect, depending, of course, of what the patients want. Because some patients will not care having a lower working memory. It depends on what they need for their daily life. But the hope is that we can better understand how the extent of resection would impact the cognitive function, so that we can discuss with the patient how far we want to go in the resection.
Very well, thank you. So thank you so much for your contribution, and we can move